Okay, so why don't we get started with the class, and more folks will join as and when the other class gets over. Okay, so here is where we had stopped. We were looking at return-oriented programming. So let me start from there. All right. Okay, so my plan for today is to quickly complete return-oriented programming, and I won't be going over all of the details, right? I mean, pretty much the exercise that we're going to be doing now at this point is to look at the stack and try to understand how various kinds of operations that would be needed, let's say for a Turing complete language, can be implemented by chaining together gadgets. Right, and I'm going to show you some basic constructs. I'm going to show you, like as I've already shown you in the last class, how to load stuff into memory. Uh, and I'm now next going to proceed to how to store stuff. I'll show you how to do one arithmetic operation, add, and I'll show you how to get one control structure. I'll stop with the simplest one of them, which is an infinite loop, and I will let you read the paper to let's say understand how conditional jumps are implemented, which is basically if then else, right? And it is a slightly somewhat elaborate construction, not complex. Rather, it involves 3 or 4 steps. So I will let you look at the paper and sort of figure it out. It's pretty much straightforward if you understand how to read assembly or get comfortable with that. So I will do that. Following which, I want to talk very briefly about heap exploits and also another kind of exploit, which is dangling pointers or use after free. And I will tell you about what is called format string exploits, and we'll stop at that for this particular topic of exploits. So if there is time, I will then start on the very first of our defenses. Okay, so that's the plan for today. Okay, so let's start from where we had stopped. Let's see. I wonder if you can see my mouse on the screen. No?
No, sir.
No, right? Okay, just a second. I don't want to do presentation mode. Let me just get rid of this. Okay. It's okay. Let me just present with this. To window. Um, you can't see my mouse, unfortunately. Okay, no problem. I will just do it like this. All right. So now you can see my mouse. Okay. So we went through this, the very first example, and the example over here was loading a constant into memory, right? And so the way you would do it is that you would place the address of the gadget on the stack, and the gadget in this case just happens to be pop edx and ret. So based upon the gadget, you can sort of figure out how to place the arguments. This particular case, you want to load the value, this particular 4-byte value into edx. So you place that 4-byte value on the stack and you proceed. Okay, so that's that. That was simple. Here's the next one which we saw. So here 2 gadgets were put into use to load a word in memory that was stored in memory into the register EAX, right? And so you find 2 gadgets that actually involve EAX in somehow. One of which is popping, let's say, the value from EAX. So that is now going to store the address in memory, except that you could not find an instruction that or a gadget that actually had a dereference from EAX into EAX itself. You just found this one, right? So MOVL EAX plus 64, dereference essentially star of P plus 64, where P is equal to EAX. And load that value into the registry AX. So what did you do? Well, you stored the value of the memory address minus 64 at this location. That's what this indicates, that if you take the value over here and you add 64, you get the memory location that you are interested in. Okay, and you load the value that is in that memory location into this register AX. So that's loading a word into memory. Or that loading a word from memory to EAX. Here is another one, and in this particular case, you are actually storing something into memory, right? You are storing the contents of a register into memory. Okay, so let's sort of figure out what that is. So you've got two gadgets, a pop, EDX, and ret. So what does pop EDX do? Well, it pops out the stuff from the stack and stores it in the register EDX. So this location over here is supposed to be treated as an address to memory. So you take whatever is here, add 24 to it, you get the location in memory that you want to store stuff to. Now, what are you storing? Well, in this particular case, you're storing the contents of the register EAX, right? You're moving the value EAX into this notation over here with the brackets essentially means you're doing a dereference, right? Taking EDX, adding 24 to it, that gives you an address, dereference that address, star of EDX plus 24 equal to EAX. That is the closest way that I can express this instruction over here in C-like notation. Okay, that's storing to memory. Now, here is one to, let's say, add something, add a particular value into the register EAX. Let's sort of figure out and work out how it goes. So the way you should start reading this gadget is always from the ESP value. So let's go to ESP. ESP says pop EDI, right? I'm reading it with you at this point. It says pop EDI and ret. So what does pop EDI do? Well, in this particular case, EDI is nothing but a register. It is popping out an address that corresponds to the ret instruction. That's what it seems to be doing. Okay, then you go to the next one. It says pop EDX and ret. Okay, so you have popped out this particular guy over here, and you're storing this value in EDX. So what are you storing? You're storing the value of this particular address in EDX, and over here you're saying add the value of whatever is in the location of EDX to EAX and push EDI. Okay, so push EDI means now you're going to push the value of the ret instruction onto the stack and now return, right? So why this particular one over here? I think it can work even without this ret being pushed onto the stack, but essentially you added the value of whatever was in this memory location into EAX. Actually, it's a good question. I really don't know why they pushed this ret over here. We should go and read the paper for that. But yeah, I mean, the net effect was that you're able to add the contents of this memory location that was in EAX to the EDX to the EAX register. So that's addition. Let's see now how to get loops. Very simple instruction over here for loops, which is here is a pointer to the gadget pop ESP and ret. So what does pop ESP do? Well, it takes the value of whatever is the top of the stack and then pushes it to ESP. And what is that? Well, that is the address of this location over here, right? So pop this and then ret. So now that points back to the same location, and then you have an infinite loop. Okay, so this is an unconditional jump and an infinite loop. Of course, if you want to implement loops that exit on a conditional, you can do it with an infinite loop and place a conditional, right? So do forever, and then you place an if then else within the loop and then break out if then else's. I'm going to leave it as an exercise for you. It's a 4-step exercise that is actually worked out in rather low level of detail in the paper. So you should actually go and try to understand how those gadgets work. Okay, and this particular paper uses real examples from libc to construct the gadgets. If you were to take a different software package or a different version of libc, your gadgets are going to look slightly different. Okay, so that's the net effect over here. Now, what this paper has essentially ended up doing is it spawned a cottage industry of essentially follow-on work to try to do similar return-oriented programming with, as we spoke in the last class, on risk architectures, on automated ways to find these exploits, right? So supposing I give you a particular attack goal, can you automatically compose the gadgets that are going to create this attack for you? So for example, imagine the shell code that we spoke about from the Aleph 1 paper. now instead of manually going through the gadgets available in libc and then trying to string them together, can you automatically write a program that searches the space of gadgets and puts the gadgets together to create that exploit, right? So there's a ton of work of this sort now over the past decade, which is why this particular paper was extremely influential and won the Test of Time award. Um, and so, yeah, so we are only touching the tip of the iceberg, but this is to expose you to the kinds of work that are going on in the security community. Okay, so that's gadgets and that's return-oriented programming. Hopefully it's sufficiently clear and I've given you a taste of things. You should definitely read the paper and understand, all of the other gadgets in much more detail. This, by the way, is the way to create or to exploit buffer overflow vulnerabilities in a manner that will quietly bypass things like WX or X protection. Okay, all right. So let me just quickly take a short detour now. I don't have a slide for this, but let me talk about heap-based exploits. But before I get there, I want to talk about something that is the other kind of exploit that we are interested in. Okay, so just a second. Okay, let's see. Trying to write. Just a second. Okay, so far we have spoken about a particular kind of exploit, which I would like to call spatial exploits. Okay, hopefully my handwriting is legible. This is the best thing that I can sort of manage. So spatial exploits are exploits that work by overwriting memory past the end of the buffer. Okay, so that's what we saw, where you write past the end of the buffer and you overwrite return addresses and so on. And we are going to see one more example of a spatial exploit with heaps in just a second. And I'm only going to give you a very high level overview of how heap based exploits work. But there's another kind of exploit which is called temporal exploits. And these are also memory exploits. And temporal exploits are exploits that work by, so as the name suggests, they have something to do with time, right? So spatial means that you are violating the bounds of the buffer. Temporal means that perhaps you forgot to do something now that is exploited later. And the most common form of temporal exploits are what are called use after free bugs. Where what happens is that you, let's say, malloc something and you free it, but then there's a dangling pointer to it. So another way of referring to use after free bugs is dangling pointer errors. Oops. Dangling pointer bugs, right? So dangling pointer bugs are bugs where you have a pointer that is that's left over to memory. Now let's say P and Q are two aliases to the same memory location, but then you did a free of Q, but then you still continue to refer to that memory location using P. So what we will see, and I won't show you an exploit right away, but it's coming when I talk about the defense, is that supposing you have such a dangling pointer, you can still do the same kind of exploits that we spoke about over here, which is pretty much the same thing. You can also the same kind of let's say you want to spawn a shell or things like that. Those are also possible. Okay, so you just have to be aware that there are these kinds of exploits. There's spatial, there's temporal. I'll give you examples of a temporal exploit, a very simple kind of a temporal exploit. But what and there are a large fraction of heap-based exploits are what are called temporal exploits. But for now, what we will see is a spatial exploit of a heap-based buffer overflow vulnerability. Okay, and then we will then talk about another kind of memory vulnerability called format string exploits, which are not related to buffer overflows, but I still want to talk about them because they give you one instance of a particular kind of vulnerability where you are able to choose a memory location, choose a value to write to that memory location, and exploit it. Okay, so let's get going with heap-based exploits that are spatial in nature. And over here, I'm going to be extremely high level because the details of how you exploit these things vary very much based upon the particular memory allocator you're using. So if you're using, let's say, the standard libc memory allocator, the way you go about exploiting it will be different if you were to use, let's say, another memory allocator. Okay, so a very high level 2 or 3 slide overview of heap based exploits is what I'm going to give you. So let me not talk about function pointer exploits. We have already spoken about them when we spoke about placing function pointers on the stack. But look at this particular case over here where you have two pointers over here which you're then mallocing, right? So you're allocating a fixed amount of space for P and Q, and the buffer overflow is over here, right? The stir copy statement where you're taking something from the command line and writing it to the buffer over here. Except that instead of this being a stack-based buffer, the space for this buffer is actually allocated on the program's heap. So as a result, the buffer overflow will happen on the heap in the sense that things like return addresses and so on are not overwritten. What's overwritten over here is actually some space that is past the space that you've allocated for this buffer P. Okay, and there's a free Q and a free P. Okay, so you might ask me, there is no buffer overflow, there is no return address to protect on the heap. So what is it that you can actually exploit? So it so turns out, and this is why I said that the exploits over here are highly dependent upon which memory allocator you use. The reason that I mentioned this is because of the way that this particular exploit works. So you should understand that when you're doing something like malloc or free, you're essentially communicating with a memory manager, and the memory manager in this particular case is in libc. Okay, so libc manages memory in the sense that when you ask for, let's say, a memory of let's say size 1024, it is going to try to allocate or it's going to try to group together memory requests that are of similar size into the same pool of memory that it's allocating from. Okay, so there are various heuristics and different memory allocators follow different heuristics, but this particular example that I'm talking about, let's assume that the memory allocator is going to manage free lists as a doubly linked list. In other words, whenever you allocate memory and you free it, right, the block that you just freed is going to be returned back to the memory manager, and it's going to be managed what are called free lists. Okay, so a free list in this particular case, you freed a block of, let's say, size 1024. So you did a P and a Q malloc, and then you did a free of a Q. So this block over here of size 1024 is going to be returned back to the memory allocator, where the block is managed as a free block, but it's managed as a block that you allocated of size 1024 in a free list. So there's a free linked list of free blocks that are being managed by the memory manager. Okay, and so the way that this, because now you're managing these as a linked list, so essentially you have to maintain the metadata somewhere, right? So the free chunk is actually managed using a forward pointer and a backward pointer, which are maintained, guess where? They are maintained at a negative offset from the actual free block. Okay, so there's a forward pointer to the next memory location where the next block of, let's say, size comparable to 1024 is stored, and a backward pointer to the previous block of similar size. Okay, so heap exploits essentially work by corrupting this particular linked list and the metadata information that's used by malloc and free. So in particular, what they end up doing is that so if you look at the forward pointer and the backward pointer, I'm going to show you some snippet of code. The snippet of code that I show you now, you're not expected to understand end to end, but I'm just showing you a snippet of code from the free list management in libc. Okay, so you can see over here that what they're doing is that they're actually allocating these pointers, and they're referring to some back pointers and forward pointers over here, and they're saying, look, the forward pointer dot back is equal to back. So they're doing a doubly linked list management over here. Okay, so the general formula for these heap based exploits is to actually inject some code on the heap And you can now, just like you injected code in the stack-based buffer, you can use the heap-based buffer to create your code and change these particular pointers, these backward or the forward pointers, to actually point to the code location. At some point, when these pointers are dereferenced, you can essentially end up executing this code. And this so turns out to be among the most common ways. This heap-based exploit turns out to be among the most common ways by which browsers are actually exploited nowadays. Okay, so browsers are vulnerable to what are called drive-by downloads, where essentially what happens is that you go visit a random website, and the random website contains a payload that then exploits a vulnerability in your browser and then takes over the privileges of your browser and uses that browser's privileges to download, let's say, malicious software from the web onto your desktop. Okay, so the way those things work are using a particular kind of exploit called heap spraying, where what they end up doing is that they end up filling the heap, a large amount of the heap, with code, malicious code, and then change essentially one of these pointers to point to one of these code segments and then start executing. Okay, so I know I have spoken about this at a very high level. In fact, these attacks are extremely complicated. I must admit that I don't understand the end-to-end mechanism of how these attacks work. There is one person who is spending a lot of time in this department understanding how these heap-based exploits work, in particular for the memory allocator in libc, and that's Ajinkya Rajput, who sits in Professor Gopinath's lab. Okay, so if things like heap exploits fascinate you, he's the person to go and talk to. He can give you a detailed tutorial of how these things work. But the high level mechanism is that they end up working by corrupting these pointers that are used to maintain metadata in the heap memory allocator. Okay, that's all I will say over here. I am not going to get into any of the details. And if you're interested, there are tons of online manuals available for this as well. But it's much more complex than stack-based exploits. Okay, so that's heap-based exploits, and it's a temporal exploit in this case. Sorry, a spatial exploit in this case, because again, as before, the way it worked was by corrupting neighboring memory locations. Okay, I will talk about temporal heap-based exploits shortly once I start talking about the defenses for memory-based errors. So let me tell you about one last class of vulnerabilities, and we will move on to our defenses. Okay, just give me a second. Okay. All right. So the last class of exploits or vulnerabilities that I want to talk about are what are called format string vulnerabilities. These used to be rather prevalent around 15 years ago. Now, not so much, but it's still very instructive to understand how they work, because once I tell you how they work, you will never think about printf in the same way. Okay, so format string vulnerabilities work by exploiting the printf statement. Okay, so what you can see over here on the screen is one. And when I talk about printf, I mean the entire printf family of functions, which includes things like fprintf, sprintf, and so on. And what I'm showing you on the slide is a particular programming pattern that is very often used in server programs. Okay, so what generally happens is that servers maintain logs for whatever reason, right? They have to keep track of the things that they did, and the logs, they actually provide a little bit of flexibility to the people who are configuring the server, so that the log can be in a format that's convenient to them, right? They might have scripts that go and analyze the logs, so the logs can be formatted according to their convenience. So that is what this piece of code over here shows. What this code essentially shows is that in the fgetS, there's no buffer overflow here. You have got a local buffer. This fgetS is filling up this buffer with the contents of something read from a file. What is this file? This file can perhaps be a configuration file that allows you to specify how to format the log. Okay, and the buffer is fed as an argument to this log function, And the log function just takes this first argument that's in the buffer and uses it as a format string, right? What is a format string? A format string is nothing but the string that you use with printf, you know, the thing with the %s, %d, and so on, that tells printf how to lay out the arguments, how to format the arguments as the argument is printed out. Okay, fprintf just makes sure that the first argument is the pointer to a file. So in this particular case, what is taken is an argument to this log file. So you know, there are some arguments that are passed over here to fprintf. It's a variable argument function. You take the format pointer, you take the format string, and the format string essentially tells you how to format the remaining arguments, and they are all stored in this log file. Okay, so the interesting question happens is what happens. So notice over here that you are actually reading the format string from the contents of this file, right? And in the good case, it's supposed to be that the site administrator, the person configuring the server, can actually specify the format string to be used within this file, and that will be read by this printf to format the arguments. So the particular threat model that we are considering over here is that perhaps there is a local exploit that the attacker has taken advantage of to go and override the contents of this file, or replace this file with something else whose contents are controlled by the attacker. Okay, so if you make that assumption, then now you will see that in this particular program, the format string is actually controlled by whatever the attacker chooses to place in that file. Okay, so what are the various possible outcomes over here? So let us go and examine that and then see what can happen. So I wonder if any of you has ever tried what happens if you take printf and give a large number of arguments of this sort without providing sufficient arguments. So let us say you do something like this: printf, you know, %d, but you, let's say, just give one integer. What do you think will happen? What do you think printf will do in this case? What do you think it's going to print out to the screen? Any thoughts?
Sir, since printf doesn't have any sort of bound check, so
Yes.
it will just take the value of whatever address you have passed at I, and
This is
then
not
it will,
address, right? It's printing out an
yeah,
integer.
sorry, whatever the variable you have passed, the value of that variable, and for the next %d, it will take the word, integer word next to I
In
mean, just
memory.
one more than I, in memory,
Absolutely right.
yeah.
Right. So in fact, what is going on over here is that printf, if you think about it, is actually a very complex interpreter. Right? Printf is an interpreter that takes as an argument. What does it take as an argument? It takes as an argument, you know, the code of this interpreter is this is the first argument over here, which essentially says, you know, this is how to interpret the stuff on the stack, and here is the stuff that you must actually read from. So the %d, and so on, these are actually arguments to the printf interpreter that tell the interpreter how to work. Okay, so it's giving instructions to the interpreter. So the %d is actually telling the printf function to go and fetch 4 bytes from the stack and print that out onto the screen. Okay, the space over here is just saying, okay, print out a space onto the you know, wherever you're printing it out. In this particular case, the command line. And the next %d is saying, look, go fetch the next 4 bytes from the stack and print whatever you see over there as you know, as an integer onto the screen. Okay, so if you continue doing this, essentially you can print out the entire contents of the program stack onto the screen. Okay, and don't provide sufficient arguments over here. So this is a trick by which you can essentially leak things out onto the screen. You can leak the values of all of the stuff that are stored onto the screen on the program stack, including the values of pointers. And we will see the effect of pointer leaks shortly when I talk about the ASLR defense. Okay, but that aside, let's move on, right? So in this particular case, the way that printf works, and you can see the diagram of the stack. high addresses are over here, low addresses are over here, stack grows this way, pointers grow this way, right? So what essentially ends up happening in this particular case over here, where I have kept the buffer as a stack buffer where you're reading stuff from the file into this buffer. It's over here. So this buffer is of length len. It's placed onto the on the stack like this, and then the log function is called, right? So when the log function is called, the first argument is passed, which is nothing but a pointer to this format string, and then there is a stack frame that's laid out for log. Okay, so now the fprintf is called. Fprintf gets called with two arguments. The first of which is, of course, the pointer to this file, and the second is the pointer to this format string. Okay, and then the stack frame of printf gets pushed onto the stack. So now the way that printf works as printf is an on the stack. Oops, have I lost a connection?
So we
Hello?
couldn't hear you for the last 2-3 sentences. Just now you're audible.
Okay, yeah, I lost network connection. I'm sorry. I don't know why I lost network connection. Okay, all right. So let me just repeat myself from wherever I think I must have been inaudible. Okay, so the way that this printf works, I think that I must have you must have lost me when I told you that the fprintf stack was laid over here. Okay, so printf, as I said, is an interpreter, right? So what does this interpreter do? Well, the interpreter, the way that it works is that it implicitly assumes that there are two pointers to the stack. I'm going to give names to these pointers. Okay, the first pointer that I'm going to use is this pointer called arg pointer, which is going to search for arguments on the stack. Okay, so and the second pointer is the format pointer that is going to point within the format string. Okay, so the format pointer is just going to point somewhere within this format string. Okay, and the arg pointer is sitting on the stack searching for arguments to interpret and print out onto the screen. Okay, so now let's say I have something like a %x, %x, %s. What's %x? Well, it just takes the next 4 bytes and prints it out as a hexadecimal number onto the screen, right? That's what it is. So what does %x do? Well, format pointer moves by 2 characters. It reads %x and that tells the printf statement what to do, right? So what it ends up doing is that it's going to read 4 bytes and then print it out in hexadecimal format to the screen. What does this do? Well, the same thing, right? It's going to print out 4 more bytes. What does this do? Well, it's going to take 4 bytes, treat those 4 bytes as an address, okay? Go to that memory location and start printing bytes from that memory location till it encounters a \0 character. Okay, so if I were to do this and not pass sufficient arguments to printf, okay, what printf is going to do is that it's going to take the next 4 bytes from the stack. If it so turns out to be a mapped or a valid address in the program's memory, it's going to start interpreting that the contents of that memory location as a string and start printing till it encounters a \0. If that address turns out to be not mapped into the program's address space, well, you will see a segmentation fault. Okay, but you can see what's going on over here, and it's rather interesting. I mean, in the sense of how you can control printf to now print stuff onto the screen. Okay, by the way, what does this stuff over here do? Let me just quickly. So what happens? Let's say if I do this. Has anybody used? Has anybody played with format strings? It's actually very interesting. What do you think this thing is going to do? %1000x.
So width specifier?
It's a width specifier. So what it will do is that it will read 4 bytes from the stack, but the output is now going to be printed in a 1000 character column. Okay, and it's going to be probably write justified, but it's going to print out 1000 bytes onto the screen. Okay, all probably just empty, and the last few locations will be filled up with the values of this integer. Okay, so it's a width specifier, and even if you just have maybe a number 1 1 and let's say a \0, you can actually end up printing 1,000 bytes onto the screen using this particular technique where you specify the width of the command line. Okay, so what I want you to notice over here, so you can actually control how many bytes are printed out to the screen. And what I want you to notice over here is that in this particular example that I showed you, format pointer is moving inside this buffer over here, and arc pointer is slowly moving upwards. Okay, in its search for arguments. And so you could ask what happens if format pointer actually moves in such a way that you can keep searching for arguments and arc pointer keeps moving up and enters into this buffer. Okay, that's certainly a possibility, especially in this particular setting where I've given you a buffer where I'm going to store this stuff. And that's how format string attacks work. So remember, that arc pointer, once it moves into this buffer, the attacker actually controls the contents of this buffer. And so now arc pointer can be made to point to things that are of the attacker's choosing. Okay, so I'm going to give you one example of how to do really bad things with this. That's coming in the next slide. But you can already see one of the bad things that has happened, which is that using this particular technique, you're able to leak the contents of memory, including the values of pointers. If there are any pointers that are stored on the stack, for example, the value of ESP, which is stored on the stack, if you were to use arc pointer to print them out onto the screen, you actually know the raw values of pointers. So remember this when we talk about ASLR, okay, and essentially how ASLR is broken. So this can serve as the stepping stone for how you break ASLR, and we will talk about that shortly, just soon after format string exploits. So you can obviously use this to leak the contents of memory. What I'm going to show you next is how you can use this same attack. So leaking contents of memory just means that you're reading the contents of memory and printing it out onto the screen. Okay, it is dangerous in the sense that you can use it to break ASLR, but can you do something more dangerous, right? What's the most dangerous kind of exploit? Well, the most dangerous kind of exploit is when the attacker can choose the memory location that they want to write to. And they are also able to, let's say, choose the value that they want to write to. Okay, so let's say they choose the memory location to write to, and let's call this M. Okay, and supposing that they decide the value that they want to write to, so choose value V that they want to write to M, and essentially they're able to do something like star M equal to V. Okay, so now if you are able to accomplish this, essentially you're given the attacker infinite power, because now the attacker can decide exactly what memory location they want to overwrite and what value to overwrite it with. And if you're able to accomplish this, the attacker can do whatever. Okay, this is the most powerful form of attack, because if you think about our stack smashing exploit, it essentially boils down to this. Right, you chose the return address and you overwrote it with the location that you wanted, which was the beginning of your shell code. Or I gave you the other example where the particular variable was used to determine which side of the conditional you went to. It was an integer variable, and if it was 0, you went one path. If it was non-zero, you went to another path. Same thing, right? If you can identify the location of that variable in memory and overwrite it with 0 or non-zero value, you can decide how the program executes. Okay, so this is the goal of the attacker, and this is the kind of the most powerful goal. This is a very generic threat model. This is the threat model for memory-based exploits. The memory-based exploit, the most general threat model that we will work with is if the attacker has the ability to choose the memory location where they want to write to, choose the value, and in some sense affect star of m equal to v. And I'm going to show you that this is possible using printf. Okay, I will show you that in the next slide. In fact, there are no details here, but I will have to explain it. Okay. Okay.
Sir, I have a doubt. Excuse me.
Yes, please go ahead.
Sir, when we say that we are able to leak the contents of the memory,
Yes.
what comes to my mind is that we also can do this via any debugger. So like what special offering does it have to give it to us?
Okay, so you can do it using debugger in the sense that you can run the program within the debugger and output the values of whatever are in memory. Okay, so in fact, can you bear with me a moment when I start talking about ASLR? In fact, that is coming right next, and then
Okay,
I will
okay,
tell you
yes,
about how
yes,
ASLR
sure,
is programmed. Okay, just bear with
sure,
me,
sure,
and
yes, sir.
if your question is not answered, then you can ask me again.
Sure, sir.
Okay.
Okay,
All right.
yes, sir. Thank you.
So let me just tell you about how format string exploits can be used to write to arbitrary locations in memory. Okay. So I've already shown you how to read stuff from memory. Now let me show you how to write stuff into memory as well. So does anybody know what the percentage n specifier is used? So percentage n format specifier is used for. Anybody
It
used
denotes the,
what's
yes, sir.
that?
Sir, it denotes the number of characters that printf has already printed up to this percent %n, and it can
Exactly.
store that value, the count, into a pointer, integer pointer that we have specified in the arguments.
Yes. Okay. So let me just show you how it works. So you take an integer pointer p. Of course, you malloc space for it and so on. I'm not going to show that stuff over here. You malloc space for it. But let's say you have a printf, and this printf you have got some stuff that you have already printed out onto the screen, maybe a percent %s, percent %d or whatever. Now, percent %n does the following, right? So whenever you read, so of course you so arguments for the corresponding stuff over here. So let's say I'll give you a concrete example. Okay, let's say you did a percentage %d and you have an integer x whose value you're printing, and now you've got this memory location over here. Now what is x? X is just an integer. Okay, so whereas p is a pointer. Okay, what will this printf do? Well, what this printf does is that, look, this integer can be of arbitrary length, right? I mean, there's a maximum integer, but this integer could be 1, it could be 15, it could be 1024, it could be whatever it is, right? So that stuff gets printed out onto the screen whenever I do this percent %d. And what printf also internally does is that it maintains a counter of the number of bytes that have been printed out onto the screen. Okay, so that counter is what is output when you do a percentage %n. And this percentage %n essentially reads the value of that counter and stores it in this particular variable p over here. Okay, so this variable p, which is an integer, now stores the count of how many bytes you have printed out onto the screen so far. So why would you need a feature of this sort? Well, the reason you need a feature of this sort is if you're printing stuff onto the screen, and let's say you want to measure the number of bytes you have printed, and you want to, let's say, do a carriage return to the next line and so on. And if you want to programmatically control printf, this gives you the power to do that, right? And so in some sense, printf itself is a very powerful programming language, even though printf format strings are very powerful programming language that you might not have thought about it in that particular way. But percentage %n actually allows you to write a value of your choosing. In fact, not of your choosing. Percentage %n allows you to write a value which corresponds to the number of bytes that you have printed out onto the screen into this particular memory location. Okay, so now I'm going to now tell you how you can write an arbitrary value into an arbitrary memory location. Okay, so that's our goal now. So I want to write star m equal to v. Whenever I write this, remember that I'm talking about m and v being of the attacker's choosing. Okay, so here is what we will do. Okay, I'm going to now show you how you can choose m and how you can choose the value. Okay, I'm back again. I'm losing network connection for some reason today. I don't know why. I'm back again, I hope.
Yes, sir.
Okay. Where did I lose you guys now?
Sir, when you were explaining about M and V.
M and V, okay. Yeah. So I have to tell you how M is chosen and how V is chosen, and essentially how the star M equal to V operation is accomplished. So there are 3 steps, right? How does the attacker how does the attacker control the value of M? How does the attacker control the value how does the attacker get to choose the value of M? How does the attacker get to choose the value of V? And how does the attacker affect the value M star M equal to V? If I show you all of these three steps, I have accomplished the attack. So let me explain that. So first of all, let me give you a crude idea of how the third step is accomplished. The third step is doing what? It's doing star M equal to V. Okay. So now let's assume format string into the format string over here. And again, okay, I'm back again. I'm sorry, something is really going wrong, and I'm sitting in the department. I don't know why. Yet I'm not able to. I'm losing network connection continuously today. Okay, so let me show you very loosely at a high level how star M equal to V is accomplished. So imagine that you were able to set up the stack in such a way that when your format pointer is looking into the string and your arg pointer is also moved into this buffer. Let's say that you're able to arrange for things so that when your format pointer is pointing to %n, your arg pointer is pointing into this buffer where the attacker has been able to place a particular address, which is in this particular case M, that he wants to write into. Okay. So now what will happen, right? So now what happens is that if we let the printf do its job and proceed, the format pointer is going to read the %n, treat the next argument as a memory location to write something into. So that's your choice of M. And remember, M is now controlled by the attacker because it is within the buffer within which the attacker has been able to control its contents, right? This is the buffer into which you're writing stuff after reading from that file. So the value of M is under the control of the attacker. So I have shown you now how you are able to affect the left hand side of the statement where star M equal to V. I am able to tell you how the attacker is able to control the value of M because the value of M is within the format string and the format pointer is pointing to %n. Okay, so that in effect allows us to do star M equal to something. I haven't yet told you how to control the value of V. So in some sense, we can check off these boxes 1 and 3, right? The attacker controls M by actually placing it as an argument within the format string itself. It gets printed out onto the screen as the format pointer is moving up, doesn't matter. But the attacker is able to figure out, is able to control the value of M by just writing it to the buffer. Now, how does the attacker control the value of V? So V is the value that I want to write to this memory location. Right. So let us say that I want to write the value 15,000 into this memory location. Okay. How do I write the value 15,000 into this memory location? Okay. So if I want to write the value 15,000 in this memory location, I need to have printed that many bytes. Printf needs to have printed that many bytes because remember the output of this %n into this memory location M is actually the number of bytes that I've printed out to the screen so far. So in this particular example over here, how do I get the value 15,000 into this pointer P? Do I have to print an integer that is 15,000 characters long?
So
does anybody have any ideas?
We can use the width specifier that we saw.
Use the width specifier. If I do this, then I have printed out 15,000 bytes onto the screen, even if I don't have an integer that is 15,000 bytes long, because it's going to print out that many white spaces. And now I know that the value of this P is going to be 15,000. Okay, if I want to print out the value 10,000, no problem, right? This is what I will do. I've printed out the value 10,000. 10,000 is bytes printf is printed out on the screen, and this P over here, the value that's going to be stored in P is 10,000. Remember the value of P over here is, this is a good case, right? This particular thing that I've shown on the screen. But what I'm talking about over here is the attack scenario where the memory location M is now controlled by the attacker, because I was able to push the arg pointer all the way into the format string. So if I can arrange for the number of bytes to be printed, so if the attacker knows exactly what the value of V should be, let's say the value of V that the attacker wants to print out to the screen is 1729. Okay, That number has a very special significance. You can actually Google it. So supposing the attacker wants to print out the value 1729, actually what he will want to print out is some address, right? So some hex address and some 4-byte value. Regardless, right? I mean, whatever you want to print is some hex address. So let's say that you want to print that value because that is now going to point out to the beginning of some shell code. You just have to arrange for your format string to have printed that many bytes onto the screen. Okay, so and because you control the format pointer and you control exactly what is printed onto the screen based upon this format string, you have control over V. Okay, so that now checks off the right hand side also, because now I know how to control the right hand side because the format string tells exactly how many bytes are printed out onto the screen. And now I've already told you how you control the value of m, and because m is already on the within the format string, the percentage n statement essentially ends up doing star m equal to v. Okay, it could be some hex address, it could even be an integer value, right? It could even be 0. Remember, I spoke about this particular code the other day. You know, if a variable v equal to 0, then do something that do something sensitive, else do something you know, that the non-root user is allowed to use, allowed to do. Oops. So this is a programming pattern that is used in some servers where, you know, you check whether the authenticated user is currently the root whose user ID is 0. If so, do something that only the root user is allowed to do. Otherwise, do something that the non-root user is allowed to do. So if you have a programming pattern like this, all you want to do is you want to get the location of this variable v in memory. Let me just use some other variable. You want to get the location of this integer variable auth in memory. So if you're able to get that, the address of that variable auth will be m, and the value that you want to write to that location will be 0, and so it will be star of m equal to 0, and you're able to effect the attack. Okay, so this is how you're able to write things into memory also. Printf is not just something that spits out values onto the screen. It can also be used to write into memory, and that's not something that many of you may have encountered before, and hopefully this will allow you to give a newfound fear for the printf function. Okay, so that's format string exploits. All right. Any questions before I move to ASLR and I sort of answer the other question that you know, I think somebody asked?
Sir, is
Yes,
it
Arvind.
always the case of format string appearing higher in the memory addresses compared to the arg
Absolutely
pointer?
not, right? So what you're saying is, you know, is the format string going to be over here, and you know, is it going to appear like this? No, 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 absolutely not. I've just presented you a very convenient case of how, you know, format string exploits can happen. You know, this same format string need not even be a character buffer. It can sit somewhere else on the heap. These format string exploits, if they are like this, they're easy to exploit. They can also be exploited in other settings, though it's much harder. I just presented to you one easy case by which you can get these things going. Remember, as I said before, one of our goals in showing exploits will be to establish feasibility, right? In this particular case, I've shown you feasibility. It may or may not be easy to exploit. In this particular case, easy to exploit. And I've shown you the tricks, the tools of the trade to exploit it. Doesn't necessarily mean that all format strings when read by the attacker. Remember, even this particular attack over here is a two-stage exploit, because you're assuming that the attacker has somehow been able to corrupt the contents of this file, which are then read by this printf statement, which is then used to perform this exploit. So it's part of a multi-stage exploit, and not always is the stack laid out like this. But if it's laid out like this is how you would go about exploiting it, right? So this, as a result, you know, because these attacks, you can see that there are many stages and many things that must be in place before the attack is successfully able to accomplish its goals. These have been considered to be more exotic and you know, less prevalent than the stack-based buffer overflows that I spoke about. That's why if you see the class schedule also, I talk about more exotic attacks, and this is one such example of that. Does that answer your question, Alvin?
Yes.
Okay. Any further questions? Okay, so if not, what I will do is I will talk about the last of the generic defenses that I want to talk about before we step into like various individual defenses. So the last defense I want to talk about, W XOR X, was one of those that is extremely popular and very widely deployed. The other defense that is extremely widely deployed that's available on all modern systems is this thing called ASLR. Let me just actually put that here because not the slides. ASLR, or address space layout randomization. And so the idea over here, the motivation over here for ASLR is very simple. It is that an attack that works with one particular instance of the program, let's say in the attacker's home machine, should not work on another instance of the program, that is, let's say, the same program running on some other installation. Okay, so if the attacker were able to reverse engineer the exploit sitting in his house and figure out, let's say, where the stack buffers are placed, what to override the return address with, and so on, that attack should not successfully work on my machine. Okay, and so the idea here is very simple. Let us introduce some randomness into the program's execution so that an attack that works in your machine will not work on my machine. So what is this? So the main motivation over here was to prevent things like worms. These computer worms, which are not so prevalent now, used to be extremely prevalent in the early 2000s. So these worked so successfully because somebody developed an attack at home, and then what they did was, the most common exploit mechanism was that they would just scan the IP address space and release the attack into the IP address space wherever a machine was listening on a particular port. So if you had a server that was vulnerable and was listening at that particular port, you would just send it out to that port, and then that server would get infected. Okay, so the motivation behind artificial diversity is that now you can ensure that the same attack will not work on all machines. Okay, so what you do is you make stack addresses of library routines, and so on, different from machine to machine. So when you start a particular process, the way that this would work is that this would work for every instance of a program. So you start a server. When you start the server, you set your random seeds, and the randomness is going to remain constant for that particular instantiation of the server. So if you start the stack at a particular location, it's going to remain the same for that particular run on the server. But when you shut down the server and restart it, the stack base address is going to be different. Okay, so address space layout randomization works by choosing random base addresses for the stack. Essentially, they work by adding random offsets to where the stack is placed. You choose random heap locations. You randomize the placement of the code segment. You randomly pad stack frames and malloc calls. So when the malloc returns a particular amount of space for you on the heap, it's not a fixed amount of space. There's also a plus minus. A plus, not always, not minus, but a certain amount of random space that's added to the size of the memory that's given back to you. You randomize the location of the global offset table. What's the global offset table? The global offset table is a table of function pointers. So remember, when I spoke about things like dynamic loading of libraries, the way that it works is that if the library is not already loaded into your address space, there's a stub of the dynamic loader that's invoked that then goes and brings the code of, let's say, libc into memory, and then fills the addresses of these functions into that table. So it's a table of function pointers that sits in your program's address space that's filled at runtime. So that's a global offset table. So it randomizes the location of that, because the global offset table is also a very dangerous location for attackers, right? If they're able to figure out where the offset table is and override those function pointers, the next time you invoke that function, you're going to invoke attacker code. Okay, so that's address space randomization, and it works by adding this random offset to these various portions. And this is actually extremely configurable. So you can choose exactly where to add your randomness to. If you just want to randomize your stack, go ahead, right? You might choose not to randomize the heap. So that's address space randomization. Now let me tell you some of the. So obviously the big advantage of randomization, address space randomization, is that an attack that works on one machine will not work on another machine. What's the disadvantage of address space randomization? Can anybody think of any disadvantages? Any thoughts? Yes, somebody has raised their hand. Shaukat, please go ahead.
I think, sir, for every memory access or
I can't hear you, Shaukat. You'll have to speak up.
You are able to hear me now, sir? Hello.
Yes. Yes,
Yeah.
please go ahead.
For every access, we'll have to add the random number, add the random number to the accesses to the memory for that particular program.
No, the random seed
so
is
that would be an
chosen
overhead.
once, and it is going to be placed to the random seed. You don't have to choose each time. The random seed is chosen once during the program initialization, so it's not much work.
Whenever. So, but when we are accessing the memory, we won't. When we are accessing the memory, we won't have to add that randomly generated number to the memory accesses or anything.
No. It's taken care of when the address space is laid out. You don't have to add that random bit each time. It's taken care of in the layout of the address space. Actually, the real disadvantage over here is that every program is going to look different. And what generally happens if your program misbehaves or crashes? Well, Microsoft programs, for example, or Apple programs, they ask you for permission to send a report back to the developer, right? To improve software quality. I'm sure many of you have encountered this. So, what do those reports contain? Those reports actually contain stack traces and so on, so that the developer can go and fix bugs and so on. Okay, so if every instance of the program is going to look different because of this randomness that you added, it is going to make life difficult for the developers. That's the primary disadvantage of address space layout randomization. Now let me actually tell you, it's not a perfect defense.
Sir,
yes.
Sir, can we say that the program startup time will also be affected by this?
Yes, but not by very much, right? I mean, in the sense that if you're, let's say, going to just add some random, spacing to the base address of the stack, it is a one-time operation that you're doing when you are starting up the program. So it's barely noticeable, right? It's probably a few microseconds right at the very start of the program, and then that's it. It is not usually something that is noticeable at runtime. Gokul has. Yes, sorry.
Yes, sir, these memory references that we have, will they be done at the load time by the loader, or will they be resolved in each memory access base address will be added, or they will be done at once while loading?
No, only the stack base address. So I'm taking the simplest version. The stack base is instead of starting at address A, it's going to start at address A plus R. Okay, everything else remains the same. So even your program does not have to be recompiled. It is an operating system level defense. It's implemented within the OS, and the randomness is added when the program's address space is laid out. Even the program does not have to be recompiled. Okay, so you not notice anything different during the program's operation, except that the addresses are going to be different. If you run the program and you print out the value of a pointer, the value of that pointer is going to be different each time you run the program. You start the program and the pointer value is going to look different.
Yes. Okay. Thank you, sir. Yeah.
Gokulnath, you have a question?
Sir, does that mean the process model we've traditionally seen so far varies for every process? The layout says.
Yes. So in the sense that it's going to remain the overall. I mean the code segment is going to be approximately where you expect it to be. The stack is going to be approximately where you expect it to be, except that it will be offset by some random amount.
So, does it also mean that the heap could be above the stack or something like that, or do they have to be in the same order?
Well, at the end of the day, right? I mean, the notion of where you place the stack and where you place the heap and so on, it is convention. So it is not really. I don't think that ASLR changes the program's address space so radically. I might be wrong, right? I mean, ASLR is richly configurable. But I would still expect that the overall ordering of these things is maintained. It's just that random amount of padding is added, random amount of mostly padding, right? I mean, random amount of padding is added to various parameters in the program's address space.
Okay, thank you.
But you might want to go and check, right? ASLR is extremely configurable. You might want to go and check what all it allows you to configure. It's publicly available. It's part of the Linux distribution now, so you can go and check. Okay, so having told you what ASLR is, let me also tell you how ASLR is defeated. Okay, and in order to do this, let's go back to our earlier slides and talk about what happens. Okay, so let's just work with this guy over here. Okay, I will use this. This is convenient. Okay, so what does ASLR do? And let's just work with one configuration option of ASLR. Let's assume that what happens is that ASLR is going to add some random amount of padding to the base of the stack. Okay, so now the stack is not going to start at a particular location. Every time you start the stack, a random amount of padding as shown by this pink box is added to the base of the stack. Okay, so the stack addresses are all randomized. So EBP is going to look different each time. ESP is going to look different each time. The exact placement of the return address is going to be different each time. And you can also assume that the code segment is randomized. So the return address itself is going to be randomized a little bit. Okay, now, as I said, what is going to happen is that this randomness that's added. So let me just put a text box over here. Let's copy. Sorry, I'm editing as we go, but this is the only way. This is the next best substitute for a blackboard. Okay, so let's just say that I added some random amount of padding over there. This random amount of padding that's added, this is not re-randomized during the run of the program. Okay, once you add a random amount of padding, that random padding remains constant for that particular execution of the program. Okay, so once you start up and once the address space is laid out, this randomness is fixed. Okay, so what does this mean? This means that EBP, if you were to run it on a program without this padding, for this particular run of the program, EBP is going to be EBP plus the value of random. Okay, that's what it's going to be, or minus the value of random. Okay, when the program is in this particular configuration. So that is how it works. It makes things hard with respect to deploying attacks widely, because each program is going to be different, but the invariant it maintains is that for that one particular run of the program, the randomness value is fixed. Okay, same thing for the code segment, right? If I was to randomize the code segment, I have to just figure out what that random value is. It could be a different random value, but once the placement of the function is fixed, it remains fixed for that one particular run of the program when the process is instantiated from the file on disk. The next time I run the program, it's going to be again randomized with different random values, but it's going to be fixed for that run of the program. Okay, so if I tell you this, can you guys wear your attacker hats and tell me how you would defeat address space layout randomization? Now start thinking like an attacker. I gave you this particular assumption that the randomness is going to be fixed for a particular run of the program. Can you now tell me how you will defeat randomness? And let's just work simple over here. Let's assume that only the stack base is randomized and I want to figure out exactly where the return address is located. The location of the return address of the stack. Can you tell me how I will be able to determine that? And the hint over here is pointer leaks, right? This goes back to printf, and somebody asked me the question of what happens, why is it so relevant if the value of a pointer leaks? So can anybody sort of think about how you will defeat this? Any people with their hands raised? Shaukat, yes, please go ahead.
I don't have a solution. I have a doubt.
Sorry?
Hello, are you here?
Yes,
I have
I
a
can
doubt,
hear you.
Actually, I don't have a solution. I have a doubt.
Yes.
Yeah, the doubt is we are whenever run libc act like that, we are taking.
Shaukat, I'm not able to hear you. Your voice is breaking.
Point.
Your voice is breaking.
I'll write it.
Yes, please write down your question on the Teams chat box and I will answer it after class, okay? I'm not able to hear you very well. Alvin, you have your hand raised?
Yeah, so if we only use relative addresses or position independent code kind of.
Yes. If you use position independent code relative addressing, go ahead, complete your thought.
Then we are not affected by the initial random offset. So
that's true. That's a very good point. That you're absolutely right? I mean, which is why I told you that, in the most general case, you can also add random amount of padding between stack frames. You can add randomness in the placement of the functions. I'm just talking about the simplest case over here, and I want you guys to help me break the simplest case, which is I've told you that I've added a random amount of padding to the base of the stack, and I want you to help me find the location of the return address on the stack. Okay, and what you're telling me is from EBP, it's a constant offset away, and that's true. But can you tell me exactly what the value of the return address would be, or value of the address where the return address will be without using relative addressing with EBP? Is there a way that you can tell me using pointer leaks? Oops. Yes, Tanmay, you've got your hand raised. Please go ahead.
Can't you just leak the pointer and then when you know the location of that pointer, use all the addresses relative to that specific pointer?
Exactly. So what you do is, supposing you were to run a program without address space layout randomization, and you were to print out the value of, let's say, ESP at some point during the program's execution, and now you were to somehow print out the value of ESP in this particular program's execution and compare the two values of ESP, the difference will tell you exactly what the random padding that was added was. And now all you have to do is you have to subtract that random padding from this particular program's execution, and you have the values of all the pointers available to you. Okay, and this is roughly how ASLR is broken. ASLR is broken by leaking the values of pointers. I mean, I've just given you the simplest case, but for every sort of configuration of ASLR, because they keep the stack, the randomness fixed, you can, if you are able to leak the values of pointers, you can go ahead and reverse engineer that randomness by just leaking the values of pointers and comparing the execution to a non-ASLR based execution, or where you control the random scene. And so that is roughly how ASLR is broken. It's not a perfect defense. Pointer leaks can be used to defeat ASLR. Okay, so again, how you break ASLR, there are a ton of hacker manuals available, but everywhere you will find that this is the common formula. You sort of go and do a pointer leak, and you're able to use the leaked value of the pointer to go and figure out the randomness. So hopefully this should answer the earlier question by one of our friends over here, who asked, what is the value of leaking the value of a pointer when you're doing printf? Who asked that question?
Sir, I asked Shashank.
Okay, is it clear now?
Yes, sir. Yes, sir. It is.
Okay. All right. Okay, good. So that is that. What is the time now? The time is 12:15. So I don't know if I have enough time to go and start my next presentation. Let me just see. Okay, so what I will do is, I wanted to actually write something on the board, but unfortunately my stylus is not working today. Let me just figure out how to do that. We will stop class early today. Next class I will start. Let me just figure out how to write with the stylus. I'm writing with my finger, and as you can see, the Jamboard looked like terrible. And we will start. So wait, somebody has a question. Who has a question?
Sir, I have Ekansh.
Yes, please go ahead.
Sir, I have a question from last lecture, that when we are talking about the boring gadgets, then why we talk about that push EVP was a boring gadget? The second
Why are
one.
you talking about boring gadget? So, you know, everything.
No, no, sir. In the second case, there were three cases of boring gadgets. The second one, push EVP red is a boring gadget. Why is that a boring gadget?
Okay, yeah. Okay, we'll take this offline. You can stay online. Let me just stop the recording, and we will go and answer those. I will.